I'm from a place called the Joint Quantum Institute. If I could show the next slide. This is a new institute. Next slide, please. That was set up just a few years ago to study quantum coherence, but apparently the words quantum coherence are missing because we don't have any blue. So I'm sorry about that. This is going to be bad because I have a lot of text that's in blue, and there is no blue here. So I'm asking again if you can try to jiggle the chords a little bit to make a connection so that we can get blue on here. Can we go to the next slide? I think a number of people have quoted from the prologue to the program of this meeting, which I think is an indication of how good that prologue was in guiding our thinking. And the quotation that I've drawn is really a question. Is there a difference between complex and complicated, such that some complex systems are not actually complicated, even though all complicated systems are indeed complex? Next. Next slide, please. So I intend to answer this question in the affirmative from the perspective of a quantum physicist. I want to also say that I'm not at all sure that the second part of this question is indeed true. That is, there's an assumption made that all complicated systems are indeed complex, and I'm not sure that that's true, but I'm not really prepared to discuss that yet, but I think it might be an interesting thing to discuss later. So part of the problem is that we've been struggling with the definitions of what we mean by complex and complicated and even simple. So I'm going to give you my definitions, and they're the ones that I'm using for this talk. I'm saying that a problem is complicated if it's hard to state what the problem is, if it takes a lot of description to tell you what the problem is in fact. I think this is very much in line with the spirit of the Kolmogorov complexity. And I'm saying that a problem is complex if it is difficult to solve. Could we go to the next slide? I'm sorry. Right. So complicated means that it's hard to state, and complex means that it's hard to solve. Now, this may not be the definition that everyone's using, but it's the one I'm going to use for this talk. So, for example, an example of a problem that is both complicated and complex is the human brain. It would be very difficult to describe the problem in the first place, to describe all the neurons, and even more difficult to describe the initial conditions. And then it would be essentially impossible, even given all of that description, to describe what happens next. On the other hand, a pendulum is a very simple thing. You only need one parameter to tell you what the pendulum is like, how long is the suspension, and then if you know the initial position and velocity, you know how the pendulum behaves after that. There's no chaos, everything behaves in a very nice way. So these are the extremes of one case, a problem that is both complicated and complex, and in the other case, a problem that is both simple and not complex. Next slide. So here is an example of what I consider to be an uncomplicated problem that is nevertheless complex. It's the Hubbard model of condensed matter physics, and the idea is that you have a certain number of lattice sites. These might be the lattice sites on a crystal. And you have a certain number of particles. These might be electrons that can move through the crystal. And in this model, you only think about two physical parameters. One is the rate at which a particle can tunnel, that is, hop from one site to the next. And the other one is, what is the energy cost for putting two particles on the same site? That is, if I have two electrons and they're on the same site, there's a Coulomb repulsion between them, and that costs a certain amount of energy. So the hopping makes things want to be everywhere throughout the crystal, and the on-site energy cost wants to spread things out so that they stay in their own sites. Now, this is a very simple problem to state. But if you wanted to calculate what happened, even at zero temperature, and you had more than a few tens of lattice sites and particles, no computer in existence can calculate this problem directly. And if the problem were even slightly larger than a few tens, then no computer that you could even imagine would be capable of calculating this problem. So why is that the case? Let's go to the next problem. The next slide, please. So this is a somewhat simpler situation. Imagine that I have n sites, and on each one of the sites is an atom, and that atom can be in one of two different states, and I'm going to call those two states 0 and 1. Now, if I've only got one site, then there are just two possibilities. The site is either 0 or 1. If I have two sites, then there are four possibilities. I could have 0, 0, 0, 1, 1, 0, or 1, 1. If there's three sites, then there's 8 possibilities. So you see the number of possibilities grows exponentially with the number of sites. If I have just 300 sites, which is a very modest number, then that means I have 2 to the 300 different states, and that number is larger than the number of particles in the universe. So what that means is that if I wanted to do a direct calculation for a problem like this, and could I have the next slide, please? The next slide shows an additional complication. Next slide, please. Yes. So quantum mechanically, the system can be in all of those states simultaneously. So that means there could be 2 to the 300 states simultaneously describing this system. And obviously, no computer could handle that calculation because the computer would have to be larger than the visible universe. So it's fundamentally impossible to calculate a problem like this. Now, could I have the next slide? So the next slide is about why do we care. Next slide, please. Okay, there's a very important problem that is like the first one that I told you, and that is the problem of electrons on lattice sites. And one of the reasons why this is a very important problem is because some people believe that this problem can describe high temperature superconductivity. Now, this is not the kind of superconductivity that I mentioned before or the kind that Professor Zikiki mentioned in his talk, but the fact that certain kinds of materials become superconducting at quite high temperatures, that is temperatures on the order of 100 degrees Kelvin, whereas most ordinary superconductors are superconducting at a few degrees above absolute zero. So high temperature is still cold by environmental standards, but very high compared to the temperatures of ordinary superconductors. And no one understands what causes this high temperature superconductivity. But some people guess that this very simple model that I described to you will explain it. And the problem is that even though the model is very simple, it is so complex that no one can calculate whether this model leads to superconductivity. So here is a model that is very easy to state, but the computational complexity of solving this model is so great that we do not know whether this answers the question of why do we have high temperature superconductivity. And it's a very important question because being able to answer that question could help us to develop these materials for practical uses, which could be very important. So could I go to the next slide? So the question is, is there any way out of this problem? And the answer is yes, maybe. There are some approximation methods, but none of them work for this problem. So that's not the way this is going to work, at least not for the moment. That is, calculational approximations have so far not been able to give us the answer to this problem. But there is a possible answer, and that is doing experiments. And it's something that I'm particularly interested in because in my own laboratory, we can do experiments to, in fact, solve the problem that you see on the slide right now. This is one where the particles are not electrons, which are more complicated because they're fermions. They obey Pauli's exclusion principle, and I can't have two in the same state on the same site, so that makes things more complex, as it turns out. the problem of what are called bosons, of which there are a number of examples in the universe. The Higgs boson is perhaps the most famous one today, but the one we use in the laboratory are things like rubidium atoms, which are bosons. It's an easier problem. We can solve the problem by approximation methods, and we can solve the problem in the laboratory by making, in the laboratory, a physical realization of the model. So it's not that we make something that is the same as some solid-state system that we think might be described by this model. We make the actual model in the laboratory, and what we find is that this laboratory model gives the same result as these approximation methods. So this gives us confidence that these approximation methods in fact work. Now the problem is, well, if I can go to the next slide, this just shows, the next slide shows some of the results from our laboratory. Could I have the next slide, please? So I won't explain what these are because we don't have enough time, but just to show that we can make measurements in the laboratory. And by the way, I should say that the measurements that we've made in the laboratory have come after some pioneering measurements made in Ted Hensch's lab in Munich that's noted at the bottom of the slide. But the point is that in the laboratory we can make a physical realization of this simple model, and we can show that it agrees with some of the most advanced approximation methods for the problem that we cannot solve directly. Now, the important thing is, if I can go to the next slide now, the important thing is that we may be able to do this slightly more complex problem, the one that has no solutions. We can also do that in the laboratory, or at least we hope that in the coming few years we will be able to make this model in the laboratory. So what this means is that we have a problem that is so complex that computationally no one can solve the problem, no one expects to ever be able to solve the problem directly, and no one has been able to come up with an approximation method to solve the problem mathematically. And we believe that we can solve the problem in the laboratory by building a laboratory model of the mathematical model and find out what the solution is. We don't know. Now, what if it turns out that this model does show that there is superconductivity? Well, then many people would say that what we have shown is that superconductivity, high temperature superconductivity, is an emergent phenomena. And I think this would fall into the category of what Jürgen Mittelstrass called strong emergence, where there is no possibility of calculating what the result is. But we know what the result is, in this case, because we did an experiment. But in a certain sense, that experiment is a kind of a calculation. So could I have the next slide? So we might ask the question, what is emergence? And the answer is, if I could have the next slide, I don't know. But I've been reading lots of definitions, and some of them seem to be more philosophical rather than scientific. And in fact, I was asked to attend a meeting, to give a talk at a meeting in which the topic was emergence at the mesoscale. And I complained to the organizers that I didn't know anything about emergence and I didn't know anything about the mesoscale. And they said, oh, it doesn't matter, come anyway and just talk about whatever you do. So I did, and could I have the next slide? I began my talk by telling people this, that atomic physicists are confirmed reductionists. We're wedded to the belief that we can understand the beauty of nature on the basis of microscopic properties in principle, and to us, emergence is just another name for ignorance. Could I have the next slide? So I softened it by putting in this, no, it was the previous slide. Yeah, okay, it didn't come out quite right. I added a little winking emoticon to try to soften the harshness of this statement, but still I believe that as an atomic physicist that emergence is just another name for ignorance. Now let's go to the next slide. So what is an emergent property? Well, here is my naive attempt at a few definitions. It's a property of an ensemble, a macroscopic property, that is not evident from the behavior of the individual parts. Now, there's two possibilities, and I think these two possibilities correspond to what Jürgen has called weak and strong emergence. One is that it's a macroscopic property that's not evident, and that no one would have been able to calculate beforehand from the microscopic behavior, but that once that macroscopic behavior becomes evident, then you can figure out how to calculate it from the microscopic properties. That's the first possibility. The second possibility, which is partly hidden here, but I'll read it to you, it's an ensemble property that cannot be calculated from the microscopic properties, even once that the ensemble property, the macroscopic property, has been discovered. And that would apparently be the situation with the Fermi-Hubbard model and high-temperature superconductivity. So now, could I have the next slide? So I pose the following question. What happens if an incalculable problem becomes calculable because I change the hardware? In other words, I've now developed a new kind of computer. In my laboratory, the computer is a bunch of atoms in a vacuum. And these atoms do the computation that no ordinary computer can do. So if a complex problem, one that was incalculable, all of a sudden becomes simple, or at least tractable, then how does this change our notions of emergence? Next slide, please. So I want you to think about another candidate for emergence, one that I've brought up before, human consciousness, that is the awareness of self and all of that implies. How does that arise from chemistry and physics? I don't think anyone knows, and I suspect that no one will know anytime soon. Some people say that consciousness is an emergent phenomena. Surely if it is, it falls into the second category of being strongly emergent. So I offer that as a candidate for strong emergence. Now, in reading about emergence, I found this quotation from somebody named Marc Bedeau, who is a philosopher. And he said, although strong emergence is logically possible, it is uncomfortably like magic. Could I go to the next slide? Now let's, in the case of human consciousness, substitute the word transcendence for magic. Now, I am a person of faith, and I have often been attracted to the notion that consciousness, whatever that really means, and I'm not sure I know, as well as free will, whatever that really means, and I don't think I know either, are transcendent phenomena. That is, they are a gift from God that are given to a sufficiently complex structure, maybe not just to humans. Now, is this notion any different from the idea of emergence? That is, is the idea that consciousness is a transcendent phenomena, that is something that has to do with the divine, is this any different from the idea of emergence, and is it any different from the idea of magic, as was indicated by Marc Bedeau? And then finally, is it any different from what I would call the old fallacy of ascribing everything that you cannot explain to God? This is sometimes called the God of the gaps. Would the notion of transcendence or emergence change if we had a sufficiently powerful computational method like quantum simulation or quantum computation? Next slide, please. So why am I posing all these silly questions? Well, the answer is simple. It's because I want to know the answers. I don't know the answers to any of these questions, and I'm not even sure that I understand what the questions mean. And I excuse myself by saying, while I think I'm a reasonably competent physicist, I'm certainly a bad philosopher and an incompetent theologian. And so I hope that a discussion of these questions will occur here in the Academy, and I welcome that discussion because I hope that it will help me to become better educated. So let me show two final slides. This is a picture. No, I did want to show those people. So if we can go back to the people slide. I just, back several slides, please. Keep going back. And one more back. Yes, okay. I want to acknowledge the people that I work with, especially in the front row from the left, Gretchen Campbell, Ian Spielman, you see me there, Paulette and Trey Porto are the permanent members of my group, and they're all working together to try to provide physical means of calculating problems that are impossible to calculate on computers. So if I could go to the next slide, and really the slide after that, and now the next one. That's the end, but I want to now invite your questions. But the fact is that this talk is more designed not to invite questions from you, but to invite answers from you. And the answers to the questions, to summarize, that I want is a question that I didn't address: can a complicated system be other than complex? What is emergence, and is it, and this I think is strong emergence, and is it any different from magic? Does the idea of emergence change if you have new computational tools that change the tractability of a problem? Is there any validity in connecting emergence to transcendence? And does making such a connection bring one back to the old trap of ascribing to God the things that one doesn't understand? And normally, I wouldn't be raising these last two questions, but in an academy where some of the members are philosophers and theologians, I feel justified in raising such questions. Thank you very much.